Thank you, Mr. Chairman. So, my name is Bartlomiej Wiendlocha, and this work is done in collaboration with Kinga Jasiewicz, Alicja Kawala, Sylwia Gutowska, Janusz Toboła. We are all from IGH University from Krakow in Poland. And today I will present you some our theoretical results concerning superconductivity in two high entropy alloys. So I will introduce you to the subject briefly, and then I will say a couple of words how can we deal with calculation of electron-phonon coupling in such a disordered materials, and present you results for two groups of superconducting high entropy alloys. This work is funded by the National Science Center from Poland. So high entropy alloys is a relatively new class of materials discovered, let's say, 10 years ago or something. And the specific feature of these materials is... So the specific feature of these materials is that they consist of 5 or more chemical elements, and even though they crystallize in a very simple structures like monoatomic BCC structure of iron or FCC structure of copper. So we have one site in the unit cell randomly occupied by 5 or more chemical elements. And the reason that they form such a simple structures is the stabilization by the configurational entropy term, which enters the free enthalpy of the material. So they are sometimes called metallic glass on an ordered lattice. So the crystal lattice is ordered by but the chemical disorder is induced by the different elements occupying the same site. And they are studied, not this way, for a couple of years because of their good mechanical properties, but also they are interesting in terms of the basic physics, how this large disorder influences the basic physical properties like superconductivity in our case. So the first superconducting high entropy alloy was discovered in 2014. That was an experimental work, and you can see the transition to superconducting state here in resistivity, susceptibility, heat capacity. So it looks like a typical BCS-like superconductor. Critical temperature was around 7.3 Kelvin. It had a specific heat jump corresponding to a little stronger coupling than assumed in the weak coupling BCS theory. So our question was whether we are able to theoretically explain superconductivity in this material, to calculate electron-phonon coupling, and to see if this is a really conventional system and what is the role of disorder in superconductivity in this case. So to do this, I have to say a couple of words about how can we deal with electron-phonon interaction in such systems. So generally, here is the electron-phonon coupling interaction Hamiltonian, and the strength of interaction depends on this matrix element G, which generally to calculate that we need a full knowledge about the electronic spectrum, about the phononic spectrum, and we have to deal with coupling of those two systems through these matrix elements. And if we have all this computed, we can calculate the strength of electron-phonon interaction, and from this matrix element we can get the more global quantities like the phonon line widths, and they enter the definition of the so-called Eliashberg electron-phonon coupling function, which depends on the phonon frequency. And from this Eliashberg function we arrive at the most important parameter for today's talk, so the electron-phonon coupling constant lambda, which is an integration of this Eliashberg function. But as I said, this calculation requires the full knowledge of electronic structure, phonons, and coupling between them. And for a highly disordered material, we have a problem especially of obtaining the knowledge about phonon spectrum, since we would have to probe many different configurations of atoms in such cells. So in fact, we need some simplifications to tackle this problem. And to do this, we may take a look at the Eliashberg function again, and we can define two parameters which will be important in the next part. So first it's a Macmillan-Hopfield parameter, which is an integral of the Eliashberg function multiplied by omega. And the second is so-called, we can say this is an average square phonon frequency, but this is not exactly the average square, but this is the name used in literature, and this parameter is also defined using the Eliashberg function, using the ratio of two integrals. And if you look on those definitions more closely, you can get the definition of lambda again by dividing Macmillan-Hopfield parameters over the mass times this average square phonon frequency. But what is the benefit of such manipulations? Because we didn't do any simplifications here, this is still an exact quantity. The benefit is that if you look more closely on the Macmillan-Hopfield parameter, you will see that because Eliashberg function is multiplied by the phonon frequency, this phonon frequency cancels out here. So this is a purely electronic quantity which may be calculated after some additional simplifications, basically directly from the electronic structure. So we don't need to know phonons to get the Macmillan-Hopfield parameter, so it may be in principle calculated also for disordered materials. And the second part, the denominator, looks like a force constant, so this is like a lattice contribution to electron-phonon coupling. And because the Eliashberg function is something which is closely related to the phonon density of states, we may even write the Eliashberg function as a phonon density of states multiplied by a parameter. And if you take a look on phonon density of states and the Eliashberg function of niobium, you can see that they are very similar, and the ratio of these two, which defines this alpha parameter, doesn't change rapidly. So in such a case, when this alpha parameter is approximately constant, you can calculate this omega square basically from the phonon density of states. So we can decouple calculation of electron-phonon interaction into electronic part and phononic part after some simplifications. And the second reason I have to do this is that if we assume the alpha parameter as a constant, we can even approximate the phonon density of states curve using, for example, Debye model. Because this, as I said, this term cancels. So a few words about our techniques. So electronic structure in this work was calculated using the KKR-CPA method, Horinga-Conroe-Stroker with the coherent potential approximation. We have the code developed in our institute in Krakow. And in this method, to deal with the disordered system, we use the coherent potential approximation in which we describe the scattering of electrons from this real disordered material as an effective scattering of an ordered medium of let's say, effective atoms. And the properties of these effective atoms are calculated self-consistently using the multiple scattering technique and the green function technique. And thanks to this, CPA brings back the periodicity. We don't have to use supercells. Every result is average among all possible configurations automatically. So we can deal with any concentration of atoms. And as I said, we have a problem with phonons. KKR-CPA for phonons is not developed, so in this work we approximate the phonon spectrum using the Debye approximation to get the omega square parameter, and the Debye temperature is taken from experimental measurements. So this is the summary of the setup used to calculate lambda for these materials. So from KKR-CPA we get the Macmillan-Hopfield parameters. From experiment we take the Debye temperature and then we calculate lambda, and if we know lambda we can calculate critical temperature. Okay, so now let's move to results. The first case is the first high entropy alloy discovered in 2014. So it consists of tantalum, niobium, hafnium, zirconium and titanium, as you can see. And this is the electronic structure, density of states of this material. Fermi energy is in this DOS peak here. And the thing which was very striking for us is, even though this material is highly disordered, its electronic dispersion relations are very sharp, so they are not smeared through the disorder, so the scattering on this disordered system is not very strong. As you will see in the second example, that will be a completely different case. And electron-phonon coupling, so here are the Macmillan-Hopfield parameters computed for this alloy, what we observed is each atomic value is larger than the corresponding atomic value in its native structure. And using this simplification for the phonon spectrum, using debye temperature, we arrived at the coupling parameter of 1, which is in the strongly coupling regime. And this value relatively good explains the critical temperature. We have to use the slightly enhanced value of so-called Coulomb pseudopotential, but this is probably related to the crude approximation for phonons. And we may say that this material is a conventional superconductor, and the effect of disorder is not very important for its superconducting properties. Okay, the second case which we were dealing with was a similar system: titanium, niobium, hafnium, zirconium, tantalum, niobium, hafnium, zirconium, and titanium, with a slightly different concentration. And the interesting thing discovered experimentally for this material was its very unexpected behavior under pressure. So it was tested up to 200 GPa, and the critical temperature increases, and around 70 GPa it stabilizes and stays at the enhanced level of 10 Kelvin. So we are interested in whether we are also able to explain this pressure evolution of TC using this rather simplified treatment. So here is the electronic structure density of states of this material. Total dose decreases with pressure, as you can see here. We observe the Lifshitz transition around 70 GPa, so this band starts to contribute to the Fermi surface at higher pressure, which was not the case at the lower pressure. This is near the pressure where the TC curve stabilizes. So this may be related to this fact. And as far as the electron-phonon coupling and critical temperature is concerned, we found several competing effects. So Macmillan-Hopfield parameters increase with pressure, but also the debye temperature increases. That was simulated using the Green-Eisen parameter measured through the thermal expansion in this work. So the Macmillan-Hopfield parameter increases, but the debye temperature also increases, so at the end of the day lambda decreases. So the lambda smoothly decreases with pressure. However, critical temperature increases because of these competing effects of increase in theta and decrease in lambda, and also because the density of states at the Fermi level decreases, Coulomb pseudopotential parameter decreases. So from these all competing effects, we have reproduced this evolution of TC under pressure. So first TC increases and then it stabilizes at the constant level. So again, we see that this is a conventional effect and well described by this effective theory. This work has been published 2 years ago. And the last case which I would like to present you today is the Scandium, Zirconium, Niobium, Rhodium, Palladium high entropy compound. This time the system is a little different. It is called high entropy compound because it's a partially ordered structure. So it has a cesium chloride structure, so it's like BCC but with 2 inequivalent atoms. And niobium occupies both of these positions, but we have a separation between these two sites because rhodium and palladium sits only on this 0, 0, 0, and scandium, zirconium only on this inside of the unit cell. And experimental work found that critical temperature change is it's around 9 Kelvin for the optimal concentration, and it decreases when we increase the concentration of this rhodium and palladium, so it decreases with X. So we wanted to see whether we are also able to explain that in calculations. We started with the question why this partial ordering takes place in this system. So we compared total energies of these two random alloy and this cesium chloride structure, and the simple energy criterion looks like it's enough to explain. Energy is simply lower if the system adopts this cesium chloride structure. And here is the electronic structure of the material. As you can see now, comparing to to the first material, the electronic structure now is very strongly smeared by the disorder. So instead of having such a sharp bands, this shading is an imaginary part of the energy which is calculated in KKR-CPA, so it describes the strength of scattering. So this electronic structure is strongly smeared because of disorder, which was not the case here. So the effect of this disorder here is much more important. So when it comes to the evolution with X, if we increase the concentration of this rhodium and palladium, density of states increases, and also Macmillan-Hopfield parameters are increasing. So what we found is opposite to what we expected here, because from the experiment, as I mentioned, TC was found to decrease with X, and from our electronic structure, Macmillan-Hopfield parameters increase. However, for this material, we don't have any information on phonons, unfortunately, since the heat capacity hasn't been measured yet. So we have nothing, we have no information on how the high temperature changes, so we are not able to calculate the lambda, but the electronic part behaves in an opposite way than it is in the experiment. So this is ongoing work. We are trying to do some more on this to see whether this trend in TC can be also explained. And with this, I would like to come to summary. So I presented you two examples of high entropy alloys. The first alloy, superconductivity in this first alloy is for sure mediated by the electron-phonon interaction. So effect of disorder is not that important here. And the second alloy seems to be more interesting, more difficult, and our initial results show that we have opposite tendency in the change of Macmillan-Hopfield parameters with concentration of atoms than TC suggested from experiment. So thank you for your attention.
I have a question about you have a disorder, a substitutional disorder basically, but isn't there one of the elements which is predominant so that this structure is ordered in a sense?
The structure is ordered. There are some, of course, we also did calculations on structure relaxation, so there are some small distortions in the real crystal for sure, and even in calculations we are able to see that there are some distortions, but we have checked that those distortions are not important in terms of superconductivity, so in Macmillan-Hopfield parameters do not see those distortions in fact. So average is like lattice is ordered.
Yes, and there's no single element which is ordered. All are disordered, basically.
All are disordered, yes.
And the second question is, at high pressure, this is very interesting. You know, there's some publications that indicate that high pressure and oxidation, for example, in oxides, is equivalent. I mean, high pressure not in oxides, but in a metal, because it changes the electronic structure. Can you see this? Can you see that?
We see, of course, we see changes in the electronic structure. Okay. With pressure, give me a second.
I give you a detail.
Yeah.
For example, the effect that has been seen is that as you go to very high pressures, electrons are localized.
Okay.
In the same places where oxygen goes when the metal is oxidized.
In this case, no. So in calculations, we don't see, of course, localization, but in experiment also, since the TC curve is flat up to 200 GPa, so you do not expect any changes like localization here.
Thank you.
Thank you.
Okay. One more question, please. Okay, I have one question for you. I saw that you have used also a KKR-CPA method.
Yes.
Yeah.
Yes. For its electronic structure, KKR-CPA, yes, we use. Yeah, it was here. No, not this way, sorry. I'm sorry. Where is my introduction slide? yeah, CPA with this ordered set of scattering centers.
Why don't try some Monte Carlo method? Because you have 5 atoms, and for sure it is quite complicated.
No, we haven't.
You didn't try?
No, we haven't tried, no.
Well, actually, I have read some recent papers people have concerning the high entropy alloys. They use Monte Carlo with some ab initio parameters.
Okay.
Size. Maybe it can be.
Thank you for this remark.
Okay. And you said that there is no disorder. I'm a little bit surprised. If you can
No,
just
there is no effect of
there is no
disorder on dispersion relations. Yes, there is of course a disorder. It doesn't move again. But what I mentioned, you can see here those bands are very sharp, so they are not smeared. Those, for example, are smeared more than those on the Fermi surface. And so there is no strong effect of disorder or electron dispersion relations. So the scattering time is like 10 to minus 13, so a typical value, I would say. This is not the case of the second material, which has a strongly smeared bands on this way. Yeah, the effect of disorder is much more important in this case. So these bands are very, very strongly smeared. So this is due to disorder here.
Okay. So you quantify disorder from electronic
Yes.
point of view. It is more the sign of semi-metallic character, I think, from the band structure. Okay, anyway, thank you very much. And
Thank you.